Okay. So the first talk today is Hugo Moeneclaey about Chatelet's theorem in synthetic algebraic geometry.
Thank you. It's a pleasure to open this second day of HotUF. And so today I will present some joint work with Thierry. And so one pair of words that is maybe a bit scary to some of you in this title is algebraic geometry. So first, let me introduce algebraic geometry very quick. So essentially, it's the study of roots of system of polynomials. That's a bit reductive as a view, but good enough for this talk. And so, then it's called algebraic because we study polynomials, right? But why geometry? It's because the main methodology is to see these roots as forming a space and then use geometry to work with those spaces. And so the result I want to talk about, it's a theorem which is due to Chatelet. And so here at this point, it's very unclear what this means, but I think a very high level view. So a Severi-Brouwer variety, it's essentially a system of polynomials. And what this theorem says is that if you have a root to this system, then you know that the space of all the roots is actually a projective space, and a projective space, it's a nice space that you know very well how it is. So essentially, this theorem says, if I have a root, I know what the space of all roots look like. And so our goal here is to give a synthetic proof of this result. So how I will proceed. So first I will introduce synthetic algebraic geometry. So it's an extension of homotopy type theory by a bunch of axioms. Then I will define étale sheaves. And we will see that being an étale sheaf is actually a Lex modality in homotopy type theory, which makes it fairly convenient to work with. In particular, we have étale sheafification. From this, we define Severi-Brouwer varieties very easily. And then I will sketch the proof of the theorem from this definition. And I think the main point I want you to understand here is that the synthetic reasoning, essentially, it's generic abstract stuff about Lex modality in hot, plus a little bit of linear algebra, but that is not too complicated. And so actually the main point of this talk, if you have one sentence you should remember, is that working with étale sheaves in synthetic algebraic geometry is convenient and helpful. The way we designed this project essentially is that we had this étale sheaf definition. We knew it was convenient and wanted to demonstrate that it is helpful. So that was how we designed this thing. So let me introduce synthetic algebraic geometry. So it consists of homotopy type theory with 3 axioms. The first one is very simple. You have a local ring R. We want to study roots of system of polynomials. So we assume a ring and we will look at polynomials with coefficient in this ring, right? Now I need an auxiliary definition to give the second axiom. So if I have a finitely presented algebra A, I can define the spectrum of the algebra simply as morphism, as you see on the slide. I think it's clearer if you see an example. So if we consider the polynomials in a variable x quotiented by p, here p is a polynomial in the variable x, then by the universal property of finitely presented algebra, you see that spec A is simply the type of roots of the polynomials, right? And spectrum like this, more generally, there are always types of roots of a system, a finite system of polynomials in a finite number of variables. And so definition, we say that a type is an affine scheme if there exists a finitely presented algebra such that X is the spectrum of A. So an affine scheme is the type of roots of a system of polynomials. Okay, and now we have the second axiom, which is duality. So it says that such a map is an equivalence. I think this axiom is best understood through 2 of its easy consequences. The first one is that the spectrum construction gives an equivalence between finitely presented algebra and affine scheme. So here we see that it's kind of a good setting to do algebraic geometry, right? Because on the left, we have algebraic object, algebras. And on the right, we have geometric object, the type of roots of polynomials. And what we have is simply a duality between the two. One remark is that in traditional algebraic geometry, to have such a duality, you have to use a fairly complicated notion of space, actually. And here we can just use types, which makes the situation simpler. And another consequence of this axiom is that all maps between affine scheme are polynomials. So here we see this is a very exotic setting in some way. And in particular, this means that we have to be anti-classical, right? Because otherwise we could define the map which sends 0 to 0 and anything different from 0 to 1, which is not a polynomial. So yeah, so we have to refute excluded middle. And then there is a third axiom. I will not say much about it, but yeah, essentially it says that affine scheme have a weakening of the axiom of choice. It's a very important axiom, but I don't want to explain too much about it in this talk. Okay, and now I can define schemes. So a scheme is simply a type which has a finite open cover by affine scheme. So I didn't define open, but you presumably have an intuition on what it means. And so the idea is that it's just a type which locally is the type of roots of some system of polynomials. And a very important example is the projective space. So here Pn is the projective space of dimension n, and it's the set of lines in Rn plus 1 which go through the origin. And yeah, and it is a scheme. Okay, so now let me go back to Chatelet's result that we want to have a synthetic proof of. So the way he phrased it, it was in traditional algebraic geometry, of course, and it was over K a field. And then a Severi-Brouwer variety, he defined them as a scheme over this field. So something which is locally defined by as roots of polynomials with coefficient in this field, such that if we see the polynomials are as polynomials in the separable closure of the field, then the type X is a projective space. Right? And then the theorem says that if there is a point in such a scheme, then it is actually a projective space, not over the separable closure, but over the base field. And so how will we phrase this synthetically, right? That's the question. So one thing which is clear is that we should say that if X is a Severi-Brouwer variety, then if it has a point, so if we have the propositional truncation of X, then there exists a natural number such that X is merely equal to the projective space. That's pretty clear. But of course, the question here is how to define Severi-Brouwer varieties. And it is not that obvious. And here the way we will proceed is that we will use étal shifts. So what are étal shifts? So first I give the definition. So I said that a type is an étal shift if for any monic unramifiable polynomials. So here, unramifiable, I will not explain precisely what it is. I will just say that separable implies unramifiable. And I will also say that you could actually just use monic polynomials and all the results in this talk would work as well. So you don't have to worry too much about it. And so what I say for any such polynomials is that if I have an element in X, assuming that these polynomials have a root, then I can actually just build an element, a unique element in X. And so essentially it means that when I want to build something in X, I can assume that any such polynomial has a root freely. So yeah, that's a relatively natural definition. And a small remark I want to make for people who know algebraic geometry is that by result of Gavin-Raith, we have a very good reason to expect that this is the same as traditional étale sheaves, although we didn't check it in details yet. But at any rate, the point is that this definition is helpful to prove result. This we know for sure. But yeah, and so first remark is that for people familiar with modalities in HOT, you see that being an étale sheaf is actually the localization at a family of proposition. So the family of propositions stating that monic unramifiable polynomial have roots. And therefore it is a Lex modality, which means that étale sheaves are well behaved in many ways. We have a process called étale sheafification, which universally replaces any type by an étale sheaf. But moreover, we even have that homotopy type theory can be interpreted inside étale sheaves. So if we have any result in plain homotopy type theory or any construction, we can interpret it in étale sheaves. And how do we do this? Well, we interpret the universe simply as the type of étale sheaves, which is itself an étale sheaf. That's true for any Lex modality, right? Then sigma, pi, and identity type, we simply interpret them as themselves because modal type are stable under sigma, pi, and identity type. And truncation, here to interpret it, we have to actually do something. So we interpret the propositional truncation, for example, as the étale sheafification of the truncation. And I write it as étale truncation, like this. Okay. So now there's a couple of required properties of étale sheaf for the rest of the development to work. I mean, beyond being a Lex modality, actually there's two of them. The first one is that any scheme is an étale sheaf. This I will not explain the proof, but that's required. And the second, which is perhaps a bit more complicated, it says that if M is a module that and that the underlying type of M is an étale sheaf, then the proposition that M is finite free is itself an étale sheaf. So that's perhaps a bit surprising to us that a proposition is an étale sheaf. One equivalent way to phrase this, which is maybe a bit clearer, is that the type of finite free module, so not finite free module individually, but the type of all of them is itself an étale sheaf. So that's an example of one type that is an étale sheaf, right? And in traditional algebraic geometry, people call those objects stacks. And it's also this property that the type of finite free module is a stack is often phrased by saying that we have étale descent for finite free modules. So if you have seen stuff about descent in traditional algebraic geometry, they are actually about higher types being a sheaf in the sense of the definition I gave. Right? And so I just need these two properties. I just need a Lex modality with these two properties for the rest of the talk to work. So now let me define Severi-Brouwer varieties and Chatelet's theorem. So for the definition, I fix a natural number n, which will be the dimension of the Severi-Brouwer variety we consider. And so we say that the Severi-Brouwer variety, it's an étale sheaf, such that I have the étale sheafification of x being equal to Pn. So here, at least intuitively, we see there's something similar to the separable closure happening in the sense that, well, a Severi-Brouwer variety in this sense, it's something that we can prove that it's a projective space, assuming some roots of unramifiable polynomials. And I just write SBN for the type of étale sheaf, I mean, the type of Severi-Brouwer variety, as indicated here. And so, okay, I will give an example very quick. So here I assume that 2 is different of 0, so that the characteristic is not 2. And for all AB invertible, I can define this type. So one remark, P2 is the set of lines in R3 going through the origin, right? So I can represent any line by a directing coefficient, which I write x, y, z. And then I have this equation which does not depend on the choice of directing coefficient because it's homogeneous. And so it is a well-defined type. And yeah, I feel so here I will not explain why it is an example because I don't have that much time. But I think the main point here is that those are not super complicated or exotic objects. It's the roots of some polynomials essentially. And yeah, and so no very important remark is that the type of Severi-Brouwer varieties for model looping. So let me explain this. So first there is this theorem in synthetic algebraic geometry that the automorphism group of Pn is PGLN plus 1 over R. I will not explain what this is. But so from this, we see that the type SBN, which was defined like this, it's actually the interpretation inside étal sheaf of the type of X in U that are merely equal to Pn, just because I interpret U as the type of étal sheaf and I interpret the truncation as the étal sheafification of the truncation. But this type of X in U that are merely equal to Pn, through usual homotopy type theory reasoning, we see that it's the delooping of the automorphism of Pn, and therefore the delooping of PHLN plus 1 of R. Right? Okay, so that's a description of the type SBN. And then we have this lemma, which is essentially some linear algebra, which say that the automorphism, so here Mn plus 1 of R is the algebra of n plus 1 size square matrices. So it's a non-commutative R algebra, right? And its group of automorphism as an R algebra is also PGLN plus 1 of R. And that inspires us to do the same construction. So we define a type of R algebra that are étal sheaf that are up to étal sheafification merely equal to Mn plus 1 of R. Those are called Azumaya algebras in the literature. And so by exactly the same reasoning, this is also an interpretation of the delooping of PGLN plus 1 of R. So here, by unicity of the loopings, we already know that the type of Azumaya algebra and Severi-Brouwer varieties of dimension n are equivalent. To conclude, we need a little bit better. We need an explicit description of such an equivalence. And here I can give it. So it's a map which takes an Azumaya algebra and return the type of left ideals in the algebra that are free of rank n plus 1 when you see them as modules. So I will not explain why this map is pointed in the sense that it sends Mn plus 1 over R to Pn, but that's also some fairly basic linear algebra. And yeah, but I will sketch the proof that this is an equivalence just to give you an idea of the kind of reasoning we do here. So we know that Li induces a map which goes from PGLN plus 1 over R to itself, going through the loop space of Zn and the loop space of SBN. Right? And just by reasoning abstractly with Lex modality, we know that for alpha to be an identity, it's enough, for Li to be an equivalence, it's enough that this map alpha is an identity. And this we can check just by computing its value. Okay. And so I need one more lemma. There's a typo here. So if I have an Azumaya algebra and a left ideal I, which is free of rank n plus 1, then A is equal to the endomorphism of I. It shouldn't be J, but I, where I is seen as an R module. And so, okay, how do we prove this? So here again, we do abstract Lex modality reasoning, and we conclude that we can actually assume that A is Mn plus 1 of R. And then it's some linear algebra with matrices. And so a corollary of this result is that if I have an Azumaya algebra and I merely have a left ideal free of rank n plus 1, then I merely have that A is equal to Mn plus 1 of R. Why? Because in this case, the endomorphism of the, since the ideal is free of rank n plus 1, the type of endomorphism of the ideal is just the type of matrices of rank n plus 1, right? And so here we have a relatively clear idea how we will conclude, right? And let me just state it. So the theorem we wanted to prove, which is for every Severi-Brouwer varieties, if it is merely inhabited, then it's merely equal to Pn. And so how do we prove this? We merely have X, so we merely have a left ideal in in A, which is the inverse of X under this equivalence. Therefore, by the corollary, it's equal to Mn plus 1 of R, and then we just apply Li to know that X is equal to the left ideal of Mn plus 1 of R. And this, actually, the fact that the map is pointed precisely means that this is Pn. And that concludes the proof, and that concludes my talk. Thank you.
Any questions? So is every algebra commutative? So why are you specifying left ideals? That's not the same thing.
So no, the Azumaya algebras are not commutative, right? Because the matrix algebra is a key example.
Thank you.
Yeah.
Questions? I was going to ask how much of this has been formalized so far.
No.
I know that the next modality easily applies a bit tricky because such an output. The classical result stated over fields was it known that it was true of non-fields?
Yep.
Like, not a generalization.
No. It was known. The generalization is due to Grothendieck, and actually the definition of Azumaya algebra is already, it's the name in the case where you generalize over an arbitrary ring.
Questions? Okay, so it's time to go to the next speaker. Thanks again.